All right, so the L5P with a blower is where we're at. We've got an 871 and a 1071, and the 1071 is currently on the engine. So we're setting up to measure mass flow into the blower, and Mario's working on that piece, right?
Yep.
We have a dual inlet to be two MAF sensors.
Mm-hmm.
What's the range of the MAF sensors?
There are 4-inch MAF sensors. They go up to 60 pounds per minute each.
So 120 pounds per minute. Okay, you might want to quickly calc up where we could go horsepower-wise with that. Basically, what I want to get here is how quickly the engine responds. The torque converter the monster truck guys use currently with the blown Chevys is really loose. And when did you feel it started to hook up that torque converter when you did the Monster Mutt test? Was that 4,000, 5,000 RPM, somewhere way up there? Because you whack the throttle in one of those with the methanol engine and you get the R's real quick. It's a super loose torque converter.
Yeah, it revs up extremely quick. We can look at RPM versus vehicle speed and see if we can pick up exactly when
it loads up?
Yeah.
Okay, we need to nail that down.
Okay.
So in the RPM versus vehicle speed, you'll see vehicle speed versus RPM starting to come together as the torque converter stall is
approached.
Yeah.
Yeah.
Okay. The term I used to use is flash. I mean, that thing, whew! So I figured with the diesel, we're going to want a similar response. So we're running the blower alone. And then I wanted to run the blower injecting methanol right at the hat. So can we get one of our straight shots rigged to inject the methanol?
Yeah.
And do we have enough nozzles? Do we get about 10 of those prototype nozzles?
Yeah, we have enough.
Yeah.
Okay. And where do we stand in terms of the methanol injection control itself, the Banks bus one? Where's that at?
It's kind of at the prototype stage, so we're starting to do beta testing on it to get a little bit more feedback on the control mechanism. And
have you written the firmware's written then?
The core firmware, so not
okay.
It's functional, but it needs a little bit more refinement. But
I figure I've been going back and forth in my head. This stuff is stacking up on top of the engine. In other words, we've got the blower. I don't want to put 4 inches of intercooler beneath it if we don't have to. And I like the idea of the methanol on top of the diesel. So we'll be looking at the methanol's ability to cool the intake air. I know on the blown engine, our intake manifold temps, by blown I mean the 540-inch Chevy, the intake manifold temps were pretty cool.
Yeah.
And we've got a bit more blower. They're running an 8. We're running a 10 initially. How much overdrive have we got in it?
20% over crank speed.
We're 20% over. The engine we're starting with has been to 6,000.
Mm-hmm. Right.
Yeah.
Yeah, 6,000.
6,300 is where it kind of fell apart in terms of the outside counterweights, and we've eliminated that basically.
Yep.
So we should be good at 6,000. The Chevy, that's the other thing I want to know with the Monster Mutt Dalmatian. How high did she rev that thing?
Off the top of my head, I think 7,000. But let me check the data log.
Let's check on that. And then when she did the sustained donut, she got it up. We were estimating the horsepower on the iDash on the Data Monster. It looked around between 1,100 and about 1,250 during that, and she did, I don't know, 15, 20 seconds like that. What RPM was she at sustained?
I think that was around 5.
Around 5,000?
Yeah.
Okay. Thing's relatively stout down there. What I'd like to do, ideally, is have our L5P, our Duramax, running in the same range and responding the same as the blown alcohol setup. So, that being the case, with a 20% over, we're going to sneak up on it and see where the boost is, and see what the outlet temperature is coming out of the blower. What's the temperature gain across the blower? What's the density loss across the blower due to temperature? And what's the density gain due to pressure? So we're going to be measuring the air density in the cell and in the manifold. So we'll be looking at the density boost into the engine. And when we turn on the methanol, I expect that to really go up.
It should.
Yeah. So the blower we're running has no Teflon.
No.
It's set up to gasoline tolerances,
Right.
I believe, rather than methanol
Gasoline
tolerances.
clearances.
Yeah. So it's kind of loose. That should be real safe.
What are your thoughts on running 2 systems on the methanol? One on top, one on the bottom.
You know, I think it'll do all the work we want it to do if we...
Just go to the top.
Yeah. I'm not worried about any hydraulic issues in the blower. I don't think we're going to be putting that much through it. Nowhere near that much. But I'd like to, if we go under and it's already basically cool, I don't think I'd rather put all of it in the hat.
Okay.
As far as distribution, do we have thermocouples on every exhaust port?
We do.
So we'll be able to look at distribution down there.
Yep.
That should tell us what we need to know. The other thing is the Denso HP4 pump that's on the L5P. Now we're starting out with a Bosch system, but I want to evolve into a Denso system. The Bosch usage area versus this is rail pressure and this is engine RPM, and the pump. These pumps turn engine speed basically as they're installed. When we get to the L5P, we're running some initial stuff in cell 2 on that killing the Duramax thing that we're doing. 3,500 looks like the maximum pump speed if we want to have 2,000 bar in the rail. If you go beyond 3,500, it gets unsafe to maintain at 2,000. I wanted to push to 3,600, but I'm into the blue area, and that kind of, I'm a little nervous about it. So we've been running 3,500, and I got to tell you what I've encountered. There is a cast aluminum Y that comes off the front of the cylinder heads on the L5P and all the earlier Duramaxes. And as it comes up and joins into a dual thermostat housing, and since we're running no EGR cooler, all the water has to flow through the thermostats, but we noticed there's a restriction and the block pressure is getting pretty high when we get to 3,500. The pressure across the water pump right now is about 50 psi, maybe a little bit more. That's a lot of head pressure.
It is.
So Mike kind of roughed out and opened it up there, and we were getting 3,500 RPM block pressure of around 75 pounds. That calmed it down and closer to 50 pounds. But anybody out there, and we'll put this into the L5P death video, that if you do a full delete and you don't modify that cooler, that duct, then you're going to have some engine overheat problems. And it also impacts the oil cooler because it flows through. So we're going to put a 2020. We're running the 17 through 19 oil cooler right now on the L5P. We're going to move it to the 2020 oil cooler. Mike's got one all ready to go on once we get the rest of the stuff done. what are we going to do for oil cooler on the monster truck engine? That's the question. I'd like to use the 2020 oil cooler, but we're dry sumping. So, Bob, could you look at how we get oil into and out of the oil cooler and run our dry sump system?
Certainly.
Yeah.
Mm-hmm.
We're gonna have to maybe make some pieces for that, or drill and tap certain areas and plug other areas of the oil cooler's oil passage. In terms of water circulation, I'm happy with what we've got.
Yeah.
I think we've run out of flow range on our coolant flow test. We're at about 100 gallons per minute, and from 3,000 to 3,500. We picked up block pressure, but we were kind of there, done on flow. In fact, I think we've got some data here. So come on around here and tell me what we're looking at, would you? So we've got RPM up to 3,500.
Yep.
Coolant, this is pressure. Where is this pressure measured?
So most of these are pressures,
Uh-huh.
and coolant temp is this guy.
All right.
Coolant flow is this guy. So that's like you suspected.
This guy right here.
Kind of flattens out there.
Oh, yeah.
I went from 0 up to 1,600.
Okay, so that's why that's straight line.
Yeah.
Okay, to 1,600. 1,600, what were your test points? 1,600?
16, 18, 2,
See the-
22.
Every 200 RPM?
Yeah.
The dots there, data points.
Oh, here's your data points. Okay. And this trace is what? Pressure?
That's pressure in and out of the oil cooler.
So pressure into the oil cooler and out of the oil cooler. All
Yeah.
right.
Right.
Not a lot of pressure drop across the oil cooler. I have noticed that the sensors back there near the aft part of the engine are pretty hot. The pressure sensors are pretty hot, even though we have them divorced from the engine. We need a little more heat shielding. Where the up pipe is, it has a factory heat shield, but we need some more heat shielding there to stabilize the temperature on those pressure sensors. But here's what's happened. That's 100 gallons per minute right there, and at about, what, 2,400?
Yep.
We flatline. But the pressure is going up. So these two don't go together.
That's for sure.
You can't be doing this with pressure and there's no more flow.
Yep. Yeah, that.
So we're out, our 144 gallon per minute flow meter is a 100 gallon per minute flow meter.
Yep.
That's basically what we've got going. In fact, it starts kneeing over right here.
Yep.
So that's probably more like 90 gallons per minute, perhaps.
Mm-hmm.
So it's pretty good up to about there, and then it knees over and it's history.
If you look at the flow trace, the actual raw data, you can see it's fuzzy as you would expect, but then when it gets up to here, it flatlines.
Yeah.
So, yeah, it's definitely
Is it a paddle wheel flow transducer? Is it an ultrasonic flow transducer? What is it?
it's a paddle wheel.
It's a paddle wheel.
Yes.
Yep.
Then the inside diameter of the tube and the amount the paddle wheel sticks into the flow are two critical things,
Yes,
right?
Yep.
that's right.
Yep.
Can we go back and make sure that's correct?
We have.
We have, and it is correct.
Yep.
Then we need a bigger flow transducer.
That's what it looks like.
Yeah. How quickly can we generate that? You know, these use nominal pipe size, metal
Right.
pipe, right?
Correct.
And then we machine and put the saddle on and put the flow transducer in.
Yep.
Yep.
Is that one that we machined to do that, or is that a buyout housing for the paddle wheel?
The pipe itself or the flange?
Well, some of those systems use a buyout section
yeah, no,
that then screws
we've
into a
made that.
piece of pipe. We made that.
You can
Yeah.
see the welds on it. We
Yeah.
took it ourselves.
Yeah, it's an in-house piece, but there's something about it's to mount on a couple of different pipe sizes.
Yes.
So we've nailed it on to, I hope, the largest pipe size that it would work on,
Mm-hmm.
to give it the the biggest flow range, but obviously it's not enough.
We actually looked at that a little earlier today. It's 2.5-inch pipe, so it should give us 300. So something's going strange there.
So we should have even more than I recalled.
Yeah.
I recalled the flow range on the smaller pipe size. So
2.5-inch pipe is substantial. Huh?
oh, I
It's a
know.
big piece.
It's
That should handle
exactly
anything we're doing there.
exactly. But we've got to modify that Y casting with the thermostats.
Yes.
We computed, in fact, Mike did earlier today, temperature of the thermostat versus how far open each one of them is. There's an 82C and an 85C stat. On the engine, it's controlling top tank, if you will, or thermostat out around 208, 209 degrees Fahrenheit,
Yep.
which is, boy, they're controlling real well. But the flow, and they're not restricting flow, the flow restriction as of last Friday was in the casting, and then Mike machined it.
And was that flow restriction intended to force coolant through the
Through the EGR cooler. So the
system?
guys that are doing full deletes plug that port going to the EGR cooler.
Yes.
Well,
right.
that's part of the water flow
Yes,
system.
Yes, you're taking that away when you do that.
Yeah. So you have to go in there and machine it out. If you look at an LML or anything earlier, the flow out of the heads and under the thermostats is totally unrestricted. So this is, the L5P is way the hell different. So we talked about blower drive. Is it on the dyno test stand?
Yes.
It's on one of them. Can we get it into the cell number 1 and start rigging it?
I believe we can. I think all the prep's been done, right?
I mean, we have external stuff we're continuing with.
Sure.
We're slowing down the 2 Bosch pumps.
Yes.
Uh,
Although we won't necessarily be doing that for the initial testing.
That's okay. We can go in.
Right.
You know,
that is our intent.
I don't
is
intend to sustain the pumps,
Okay.
overspeed the pumps for a sustained period.
Then we should be all right.
When do we get the bigger pulleys?
We have the pulleys. It's the hubs to adapt the pulleys to the CP3s that need to be machined.
So you've designed something up yet?
Yes. Yes.
So is it going to go over to the machine shop?
Yes, the drawings have been sent to Manny.
When can Manny fit them in?
That I don't know.
Let's check on that tomorrow, and it would be probably quicker over there.
That was.
And we're
my
doing
thought.
more than one,
Yes.
so
This is how we did it when we originally adapted the smaller pulleys to the CP3s. Our own shop did the work, so
yeah.
that was the
Okay,
path I
well,
was
we're
taking
good
it,
then.
yeah.
We'll now have a CNC program to
Yes. Yes,
do the
certainly.
pump adapters.
Right.
So we're going to slow them down to what percent of crank speed?
I think it's approximately 60-something%. I will have to go
That
back.
sounds good.
I'll have to go back and look at the
I mean, if
numbers
you
again.
use 3,500 as the limit, let's
Yes.
say 3,500
Of
RPM.
engine RPM.
Yeah, and we want to turn the thing 6,500, somewhere in there. We're still going to be crowding the limit.
We will, yes.
Yeah.
I think with the 40-tooth pulley, you can go to about 6,200 engine RPM and be within the reasonable range of the pump speed.
Got it. Good. That's what we're looking for. That's perfect. I want it to work. I don't want to slow them down so much
Right, right.
if they don't work downstairs.
Uh-huh.
As far as the dry sump system, we've got a dry sump tank. We've got to figure out where we want to put that in the cell.
Yep.
Do we want to make a stand for it? How do we want
We were
to?
thinking about attaching it to the dyno cart.
I like that. Yeah,
I think it'll look clean.
yeah, that'd be very.
For the previous application, I had built a vertical post that mounts the tank, and Mike was looking at maybe we could take that vertical post and mount it to the test cart.
Well, make sure you triangulate. It's going
Yes.
to be vibrating.
Oh, yes.
That's for sure.
Yeah, it's going
And
to need to be
because
stabilized.
It's almost like you're mounting this dry-sump tank on the engine. So I'm not real comfortable with that. But in the monster trucks, they're hard mounting the engines.
Yes.
So if you're on a chassis tube, you're probably vibing almost as much as this would be.
Certainly.
We do want to run aeration tests on this. I know the dry sump tank is supposed to really separate everything real well, but we need to rig a petcock so we can pull a sample, aeration sample. I want to make sure this whole system, we keep the aeration below about 7%. 5% is my goal. 7% would be acceptable. We've talked about the coolant. We've talked about the coolant flow coming out of the heads. Do we want a thermostat? The monster truck. To me, it aids with warm up.
It does.
And Bob and I were talking about coming out of the heads and doing a thermostat housing. With the twin stats. What do you think of that?
We can try that.
Okay. So, I'm looking.
We may also look at the possibility of using the Y casting if it's acceptable.
If you could fit it in there with the drive system, that would be the slick way to go. You can't use anything earlier because the front of the heads are different.
Yeah, so
The water comes out of a round hole now, as I recall, versus
it's got to be L5P dedicated.
Yeah. Yeah. Ultimately, L5P dedicated. So, if it works here, that engine, our dragster engine is an LMM, isn't it?
Correct.
Yes.
Yeah. So,
It's going to be a little different.
yeah. Edelbrock has got a cast aluminum head that's early architecture, but no big valves,
Nope.
no porting, nothing. So I'm thinking, Mike, why don't we work on port shapes for the L5P?
Okay.
If you can get into that and start working that, I'd like to.
Sure.
And to the extent that I'm just talking about working the stock valve sizes. We could go 33. They're currently 31 millimeter intake and 33 intake and 31 exhaust.
Right.
The exhaust port, if I recall correctly, flows a lot better than the earlier
It
heads.
does quite a bit.
Yeah. And the intake ports are quite a bit shorter. So getting in and porting them, at first you'd think that it would be easy, but those end ports are
Very difficult.
very difficult. So we're talking about milling the end of that rectangular opening on the L5P head to get a straighter shot at the port. But whatever we bolt to that, how much O-ring width are you looking for, Bob? I mean, you want to run an O-ring diameter
Well,
of,
typically a 3/32 O-ring
and you're happy
cross-section.
with it.
I think that would work well.
Yeah. Was there something wrong with the O-ring grooves on the pre-production diff covers?
I am not aware of any of that. I don't know.
That's supposed to be a square corner. I think they got machined into a radius.
So they don't squish as much.
Yeah, we're supposed to be talking about the super turbo. Let me get back to that.
Oh, you mean in terms
Of the cross section.
of the cross section
Yeah.
of the O-ring groove? I have not heard anything about that,
Yeah.
but certainly that would not be what you'd want to do.
Yes. And we got to tune up the powder coat. It was kind of,
I see.
we got about 10 of them powder coated and machined them, and the powder coat is kind of lumpy here and there. That ain't going to fly.
No, we don't want
So, back to the engine. If we could get it into the cell and start rigging instrumentation, will it compromise the rest of what we want to do on it? I
I
mean,
don't think so.
so tomorrow morning? if we can start moving that way, Mike, if you want to start working on porting.
Sure.
Now, it'd be nice to take an L5P head and pop out the exhaust seats and
Go to a bigger seat.
go to bigger seat. Yeah.
Yeah.
If anything, I'd like to get the exhaust flow to equal the intake flow. That, to me, with a turbocharged engine, you're boosting in and you're restricting out.
Sure.
If we go to bigger valve with the same valve timing, we can flow more mass out the exhaust side if the port will go along with it.
Okay.
You see where I'm going?
I do. Yep.
Yeah. I mean, the first thing we want to do is clean up the valve pockets on the intake and maybe go to a set of 33s on the exhaust. That should clear a stock bore, and we could test on a stock bore engine. I really like the L5P pistons because they have that laser enhanced rim on the combustion ball.
Yep.
That makes the melting temperature
Slightly higher.
slightly higher. I don't know what slight. Do you know what slightly
No, I
means? So I mean, is that 20 degrees or 100 degrees? So the other thing I want to do is, and we have no problem with a dry sump, but when we on the nozzles with a dry sump, we can remove the restrictors. So the L5P nozzles are almost exactly, or they are exactly, the production ones are the same as our race ones.
Same.
Yeah,
Yeah, within a couple of thousand, but yeah.
within a couple of thou.
Yeah.
So they should flow the same as our race nozzles currently do, and that's the stock nozzles.
Correct.
The question is, can we build an enhanced nozzle to flow more? I want to go as far as I can go with a stock L5P pistons.
Okay.
And then the ring pack. If you could give me the specs on the stock ring pack.
Sure.
What are we looking for? If the rings are light enough and the gas pressure works enough, we might be able to turn that damn thing, those pistons, 6,000 RPM. Are the wrist pins the same diameter as the LML and earlier?
I believe they're different.
We need to check that.
Yeah.
Because we need to make a set of our rods. What we're going to do is put our LML and earlier billet crank with the big pins in the L5P engine. We're moving the crank trigger off the back of the crank to the front of our vibration damper.
Yep.
So we're putting teeth, we're going to machine teeth into the back side of the vibration damper and put a crank position sensor on the outside. I like the hell out of that because otherwise you got to machine part of the rear counterweight away, and you've got a 3-bolt mounting set that GM does, and one of the bolts is on the crank arm, and then 2 of them are into the counterweight, and the counterweight is partially machined away. I want all the counterweight I can get back there. So I want to get as close to zero as we can, and if we have to put a little counterweight still on the outside, I'm not afraid of that. I just don't want it to be excessive.
Sure.
So as far as the action items are the vibration damper design for the L5P front trigger. We're going to run the 2 precision turbos that they gave us, and we'll do all of that on this LMM. But I think this block is stronger on the L5P as well. And I'm hoping the deck is part of that because the design peak firing pressure on the earlier engines is 150 bar. On the L5P, it's 180 bar. A little over 180 bar.
183.
183. And we've been to 195. Have we been over 200?
We've been over 200.
Yeah. We've been over 200, not for any sustained period of time, but we're putting the firing pressure to it right now. So I think that's all I can think of. I just want to get that thing in the cell because the whole state of mind changes when the engine goes into the cell. and we start getting the instrumentation rigged and bugged out and all of that while the guys are finishing off what we're doing on the outside of the engine. The blower hat that Mario is building right now, how's it looking? Is he getting there with it?
Looks like an Enderley barn door with no throttle.
Oh, does it really?
Should be done either tomorrow morning, I think.
So we're putting the two mass flow sensors vertical. Got it. All right. And then we need a plate. I don't think the bottom plate is thick enough to put the nozzles in.
Oh no, but would you?
Well, you can put them in the walls.
Come in the wall because the walls right now are a good 3 inches tall.
Yeah, let's put them in the walls.
That's what I would think.
Why don't you figure out how you want to, you know, that thing's got twist in it, so it's working the air axially.
Yes. How many nozzles were you considering putting into that?
4.
4?
Yeah. Now the nozzle flow rate can be moved all over the place.
Sure. Oh, certainly.
You know, because we're
Certainly.
we're not using the normal water meth tobacco shed humidifying
Right,
nozzle or
right.
something like that,
Uh-huh.
which works okay, but if you want to change the nozzle size, you got to unscrew them.
Yes.
So what we're doing is I don't know if you guys knew this, but we've worked out a nozzle for our water meth systems that's methanol impervious. So that being the case, we're going to try them on straight methanol.
And is it eighth pipe thread?
No, it's a
Rather
normal
than quarter?
fuel injection type
We got some adapters
that
on
are
there.
pipe thread, I
Yeah,
think.
quarter pipe, I think.
Oh, so it's an O-ring seal? That type of thing?
Yeah.
And how big of an O-ring approximately?
Oh, it's got an adapter already, so it will capture the injector, and then I think it's actually a 3/8 pipe. So we can just put a 3/8 pipe bung and screw it into the.
Okay.
So the adapter that we've designed captures the injector,
Uh-huh.
and you put fuel right into the top of that
All right.
adapter.
All right.
So that feeds the injector, so you don't need a fuel rail clamped on top
Okay.
of it.
And what kind of a spray pattern does it put out?
Conical.
It's a conical.
It's a conical.
So we want to
What's
angle.
the- we have
want
two
to
different-
angle these down into airflow.
I would.
Yeah.
And he's got a design with a 45-degree angle already on it.
Okay.
So have we machined any of those out of aluminum?
We have, I think, straight ones, so we would need to do it.
Well, we can angle cut them.
Yeah.
Yeah, we can mill the end at an angle with 45. I think 45 is a pretty happy angle.
Okay.
You know, considering how far up. What's the cone angle on those injectors?
30 degrees.
Okay.
So it's a pretty
fairly
tight
narrow.
angle. Yeah.
Yes.
There's another one with a bigger cone angle, I think.
I think that one might be like 20 and 30.
Oh, it's tighter.
Yeah.
Okay.
Pretty.
But it's not 60 or 80
No,
degrees.
and that's just the opposite of what the manufacturers of the nozzles are usually looking for. They're trying to increase cone angle to cover more surface area of whatever they're
Yeah.
cooling. So they're usually used for cooling. But that
We
30
kind of
degrees
see
sounds good.
using these nozzles on a duct, like a boost
Uh-huh.
tube.
Yes,
If you wanted to do that like between the intercooler and
certainly.
the engine, on our monster rams, we're going to have to change the nozzle architecture for those as well. Right now, there's 2/8 pipe targeted nozzle ports
Yes.
on that 6.7 Cummins
Right.
monster ram.
Right.
Do we need 2 nozzles? Will 1 suffice?
Mm-hmm.
But they've got a real big dynamic range of flow,
Okay.
and they'll turn down to almost nothing and still atomize nice, which is another thing you don't get with the older style nozzles. So, and you're pulse width modulating the nozzle. You're not controlling the speed of a pump to change the flow rate, which is not as quick as PWMing the nozzle, where the next pulse, you know,
Is
what you've
Is
changed.
a change in duty cycle?
yeah. So it's lightning speed adjustment.
When you mentioned about the dry-sump system and going to the 2020 oil cooler,
Yeah.
What were your thoughts on the fact that we have 2 pressure stages on the dry-sump pump?
Where do we want to go with those?
Yes, where do we want to go
on
with
the
those?
earlier ones, we go in the traditional oil inlet,
Yes,
which would be after the oil cooler.
right,
And then on the other side, we go in the front of the block.
right. And I believe that opening is not available to us on the L5P.
It's now on the side. There's a drilled and tapped opening that I think it's 3/8 pipe or something like that.
Is
you
that
recall-
on the right or left bank of the engine?
That would be on the right bank of the engine, down near the pan rail and clear at the front.
Okay, uh-huh.
If you look at that one,
So below the area where we had introduced oil before.
yeah, it's, I think it's feeding the cooling nozzles, and I don't know if it's feeding the mains as well on that side. We'll have to,
Okay. Okay,
I can't remember the oil
But
flow
that's-
schematic in that block.
that's the area to look at.
Yeah.
Okay, all right,
So we're going in both ends of the system.
which is what we did before.
Yeah,
Uh-huh.
I like that because it keeps a more consistent pressure through
Sure,
the whole system.
certainly.
Yeah, better for the front end of the crankshaft too. We need to get the wrist pin down. You've already determined the center distance on the rod. The deck height on the L5P is 4 millimeters higher, I believe.
Little, yeah, over.
So we're going 4 millimeters more rod length. We're going to let the pistons hang out
13.
13th thou or so, and I don't know the compressed height on the gaskets.
It's like 38, 39.
Yeah. So, but I love the looks of the piston. This is the best production piston I've ever seen in a Duramax. So, that being the case, how far can we go with it is the only other question I've got. Will it run in a monster truck engine? Will it run in a marine engine, sustained full power for hours? That's where we'll go with what we're doing right now on the pump, in Dyno 2. Last thing, Walt Ware has been working on with Froud in the UK on a new absorber and control system for Dyno 2. They'll take us steady state full load. I think it's about 3,600 pound-feet and 2,000 horsepower steady state full load. Flash readings are probably going to be 3,500 to 4,000 horsepower and maybe approaching 5,000 pound-feet of torque. It's bigger than the F24 that we've got, in Dyno 1.
What's the max speed?
Max RPM, with oil mist cooling, 9,000 RPM. I'm loving it.
You have some
Yeah. Well, we're going to find out how far we can buzz a diesel here in this whole process.
Cool.
But, our ECU is done at 8,000 RPM. The dyno's done at 9,000.
Yep.
But if we did some badass twin-turboed big block or Hemi, methanol engine, we could run it in there and sing it for a while. So that's quite a, the one that's in Dyno 1 is, Superflow calls that a Black Widow, their version of that a Black Widow. But ours is painted traffic blue. That's what Froud calls that color.
Oh, really?
Yeah, so our new Froud will match the old one.
Okay.
Yeah. And the controls on that ought to be way, way, way more refined using a Froud controller on a Froud dyno than using a Superflow on a Froud dyno. So, hope I can afford it. They're real proud of those things. And the dyno itself weighs 1,990 some pounds. Just getting that in the dyno cell and putting it on our rail system, that's going to be a treat. We got a forklift that will cantilever that thing out there like that
Ocean going.
and go through the door. Getting that thing in the dyno room is going to be fun.
Yes.
Yeah, we might need a machinery moving company to get that
Well,
thing in there.
They could probably take care of that.
Yeah,
Don't forget your steel-toed boots that day.
Yeah.
everybody's got to wear their steel-toed boots that day.
Yes.
Yeah. Okay, guys.
All right.
The blown motor's going into Dyno 1 tomorrow.
Cool.
All right. Thank you. And you guys at home, I hope you're enjoying this. We'll be making some noise and showing you some results and sharing it all out. Anyhow, stay tuned.